Good morning. Today's topic is inductances of coils. In the last lecture, we have discussed about Faraday's laws of electromagnetic induction. We have seen three different cases when B was moving. Case 1, B was varying and conductor was stationary. And we have seen B is constant with respect to time, whereas conductor is moving. And we have also seen that B is varying with respect to time and conductor is also moving. So for each of these things we have seen what is the EMF which is induced in the conductor. This is what we have discussed in the last class, and also we have also solved problems on this one. In today's class we will discuss about inductances. So we will discuss about self and mutual inductances, and also we will try to determine the self-inductance of a solenoid. You know that solenoid is just like a bar on which there is a coil wound on it. So we will determine what is the self-inductance of a solenoid. Now, coming to the introduction to inductance, you might have studied about this inductance from your 10th class. A quick review. Inductance is the tendency of an electrical conductor to oppose any change in the electric current flowing through it. Any current flowing through a material, if it opposes the flow of current, if it opposes the current, then that property is called as resistance, right? Resistance is opposition to current. Whereas if it is opposition to change in current, which means if the current magnitude is constant, there is no opposition. Only if there is a change in magnitude of current, then only it is opposing. Then that property is called as inductance. Okay, and it is represented by the symbol L. L is used to represent the inductance, and it is measured in Henrys. Henry, normally referred as H. Okay. Now, the equation. Inductance is defined as the ratio of induced voltage to the rate of change of current causing it. So the electronic component designed to add inductance to a circuit is called as an inductor. You might be seeing inductors in your laboratories also. So the inductance basic equation in a circuit is normally given by the EMF, ratio of induced voltage to the rate of change of current, which means it is equal to EMF by rate of change of currents. This is the equation for inductance, or I can write this one as EMF is equal to L di by dt. This is the equation, governing equation for an inductor. Now, what are the factors which affect the inductance of a coil? So the factors which do affect the inductance of a coil is, before we discuss about this thing, let us first move on to the inductance types, which are self-inductance and mutual inductance. So what do you mean by self-inductance and the mutual inductance? See, let us suppose when there is a coil, when there is a change in current in this one, then automatically, say whenever a current is flowing in this one, automatically you can experience a magnetic field around it, isn't it? So automatically there will be a magnetic field adaptance, right? So if I is a function of time, then automatically the phi also will be a function of time, right? So any time varying current will develop a time varying magnetic fields, right? So now surrounding this one, it is a time varying fields. Now this, you consider it as a conductor. A conductor placed in this magnetic fields, which is time varying, automatically develops an EMF, right? This concept is called as self-inductance, which means EMF is developed, is generated due to the current in the same coil, which means the same coil carrying current, same coil developing flux, and this same flux is linking this conductor. So in the same coil, EMF is developed. So this phenomenon is called as self-inductance. Okay, so where is its current coming from? Might be some battery or might be some source, right? So this V. So this V is developing a current. The current is developing, this current is developing, V is developing a current, provided there is a closed circuit. This I is developing flux. Flux is developing EMF. This EMF, it opposes the very cause of it due to Lenz's law. Now this is the concept, and this is called as inductance or self-inductance. It is all happening in the same coil. Okay. Now the flux which is given by this one is given by Li. Okay, so L is normally given by phi. Let us suppose if it is varying, then I'll take it as d phi by dl. Okay, so the self-inductance of this coil is equal to the number of flux linkages which are developed by the current which are aligned into the circuits. Okay, now this inductance is now dependent on the cross-sectional area of the coil, the permeability of the material, and also the number of turns. The higher the number of turns, the more the number of flux linkages will be. Now we'll get back to the terms now. So the first one, inductance is greater when the number of turns of wire in the coil is greater, because more coils in the wire indicates greater amount of magnetic field force will be developed there. The second one is coil area. If coil area is higher, then automatically what happens, the inductance also will be higher, because you will be getting a larger area for developing flux. The next one is core material. There are some materials which usually they will allow magnetic field to pass through them. So ferromagnetic materials, they are more magnetic in nature. So those materials, they will add to your self-inductance. The last one is a coil length. This is quite opposite. If the coil is having a very long length, then automatically the inductance will be reduced. Okay. So these four factors do affect the self-inductance of a coil. Now the other case is a mutual inductance. So what is mutual inductance? Now let us suppose I'll take two coils here. Now let us suppose here I am giving a V. Now there is a current which is flowing. Now I'll consider that this V is time varying in nature and I is also time varying in nature. So it will develop a flux, isn't it? When a current is flowing through this one, it is developing a flux. Now this flux is linking, I'll assume that the flux is linking both the coils, coil number 1 and coil number 2, isn't it? Now when the conductors are linked with this time varying flux based upon Faraday's laws of electromagnetic induction, case number 1, this is a stationary coil which is linked to a time varying magnetic field. Automatically what happens? EMF is generated here and also here, because this is also linking this flux. So both the EMFs are generated, right? So case 1, it is called as self-inductance. Case 2 is called as mutual inductance, because the current is not flowing in the second coil, current is flowing in the first coil, field is developed by the current of first coil, but EMF is generated in the second coil. In this case it is called as mutual inductance. In this case it is called as self-inductance. Understood? I hope now you have understood what is the difference between self-inductance and mutual inductance. Now moving ahead, how to determine the equation. We know that EMF is equal to N d phi by dt. Right? This is what we have seen in Faraday's law. Now what I am doing is, I'll keep this one like this. EMF is equal to N d phi by dt, right? So what I'll do is, I'll multiply and divide with di. And I'll rearrange it. So this is d phi by di. I'll write this one here and I'll write this one here. This is di by dt. Right? Now, this is EMF, right? This particular term is considered as inductance. Right? So, now this will reduce to EMF is equal to L di by dt. Yeah, so now L is equal to N d phi by dt. Okay, this is the expression which we generally use for computing the inductance. Okay, now you can simplify this expression also. Let us suppose if the flux is independent of I, then you can write it as N phi by I. Okay, now you can still solve this equation, you can still simplify this equation. Now let us suppose if you do have a solenoid. Okay, you know that there is a solenoid. What do you mean by solenoid? A solenoid is just like a core on which there is a coil which has n number of turns. So you know that the magnetic field intensity, when there is a current I flowing in n turns of the solenoid which is having a length of L, the field intensity of this one is given by H is equal to Ni by L, right? So for a solenoid, then what is B? B, you know it, mu H, right? Mu into Ni by L, right? Now what is flux? B, right? Flux density into area. So mu Ni by L into A. Now when I know the flux, what is inductance equation? Inductance equation is N phi by I. I am considering everything is independent. So instead of taking N d phi by dA, I am considering N phi by I. So I'll take N by I into phi is this equation mu N I A by L. I will get cancelled. So inductance is equal to mu N A by L. Sorry, mu N into N square, mu N square A by L. This is the expression for inductance of a solenoid, self-inductance of a solenoid. Understood? So, I hope now you are able to differentiate self and mutual inductances and explain them in detail, and I hope that now you have known this equation of determining the self-inductance of a solenoid. I hope now you will apply this one to determine the inductances of a solenoid in the class. Thank you. Try to solve this particular problem. See, in this one, determine the inductance of the solenoid. You know the inductance of a solenoid, either you can use N d phi by di, or if phi is constant, then you can use N phi by I. Or if you do have area of cross section and length, you can utilize this formula for determining the inductance. See now, determine the inductance of a solenoid. 2500 turns, N has been given, wound uniformly over a length is given, and this is cylindrical paper. Diameter means you can determine the area. So N, L, A are being given. Medium is air, so mu value is also given. So you can employ this formula to determine the inductance. Try to solve this problem before coming to the class. Okay, thank you.